involved in the initiation process. In bacterial cells, right, once we have initiation and we give the elongation factor, or rather than initiation factor, they're called elongation factors, EFTU. So this means elongation factor TU, and that's the gray guy. So that's equivalent to the initiation factor. And you notice it has a GTP bound to it, and it's bound with the TRA. So this is pretty much the same condition that we found during initiation. Only now this elongation complex is moving into that A site. Y'all see the similarity? Okay. So the question is, why is it there? And what happens is, remember, these TRAs can move in and out of the site. And they're selected. How are they selected for the right one? Yeah, that complementary between the codon and the anticodon. So as these TRNAs are bouncing in and out of that A site, they're testing that complementarity. And that complementarity is only between three nucleotides, right? It's only between three nucleotides. So it's not very stable. It's not terribly stable. And with wobble, it makes it even less stable, right? It can pop in and out. So the tRNA pops in. If it's the wrong one, there's no complementarity, and it pops out. And that process keeps going until the right one comes in. When the right one comes in, there's just enough complementarity. It's not terribly stable, but it causes it to pause for a small amount of time. Okay? Pause just a small amount of time. And as it pauses in that site, one of the ribosomal proteins in the large subunit, one that we do know the function of it, activates the GTPase. This little molecule here, this elongation factor, is a GTPase. It can bind GTP and it can hydrolyze it to form GDP. But it's not very good. It's kind of a cruddy enzyme, and it needs help. It needs what we call a GAP protein, GAP, which stands for GTPase activating protein, GAP. So when the GAP protein interacts with this GTPase, it activates it, it gets it either turned on or it stimulates the GTPase activity. Make sense? Question? Okay, so now this guy's popping in and out. When the right one pops in there, he's held in there just that split microsecond longer because of the complementarity, long enough so that the GAP protein in the large ribosomal subunit can activate this GTPase and cause the GDP to hydrolyze, or the GDP to hydrolyze and become GDP. We all know that when you change that phosphate, you add or remove a phosphate from a protein or a protein complex, it has to change conformation. The protein has to refold to accommodate that. You can see here, even if we start in, this GTPase has changed shape. And when that protein undergoes that conformational change, it no longer has affinity for the tRNA, right? And it pops out, leaving the tRNA site. Once that elongation factor is gone, this tRNA is kind of locked in the site. So this complex, and in this case EFTU, and in the case of initiation IF2, right? Those two complexes essentially are screening or proofreading or checking for the proper tRNA to be inserted into the A site. That's the function of that. Now notice that requires what? One GTP. So already protein synthesis requires one GTP. Okay? So this protein here, EFTU, this protein is the elongation factor. Prokaryotic cells, it's the most abundant protein in a prokaryotic cell. Remember, these guys, every time their function in life is to replicate quickly as they can. Every time they do that, they have to duplicate every part, every one of their components. And they have a lot of protein. So they're constantly pumping out protein. This is the most abundant protein in the cells. IF2 is not the most abundant protein. Why is IF2 not the most abundant protein? Why is it not? It's not anywhere near as abundant as EF2. Why is that? EF2.
It's just it's
It's degraded? No.
You just need
It's a simple question.
You just need it to start. You don't need it for every single thing.
Yeah, right. You have a huge protein. You only initiate once. But every single amino acid is added after that. You need this elongation factor. So there's a lot more of it, not as much IL-2. Okay, so once that gets there, once that happens, right, then what happens? So this factor here is sort of an interesting guy, and we're not sure exactly how that works. This is EFG, not EFTU. And EFG is what we call the real elongation factor. And what EFG is, it has a GTP on it, right? And notice it's going into sort of that, it goes into that half site, into that A site where there really is not, it's in the A site in the large subunit, but not the small subunit. Gets in there, it hydrolyzes that GTP and comes out. It's involved somehow in the translocation of that, right? It's the real elongation guy. It's doing this movement, where it's moving the ribosome and the message up there. It's absolutely essential. You have to have EFG. Right? These GTP work. So look at there's hydrolysis of GTP. It causes a conformational change that moves the tRNA from the AP hydrogen site to the P site. Second GTP. So far, we've needed 2 GTPs for protein synthesis, 1 for initiation and 1 for elongation. That's all we need. Why is that all we need? Why don't we need another? GTP is just a high energy molecule. Why don't we need another one? Do we need another one to make a protein? Kind of a dumb question, but remember, what about the peptide? We gotta make a peptide bond. Does it need energy? Well, it does need energy, right? There it is right there. It's in that high energy acyl linkage. This guy here, once you activate this and make that linkage there, that's a high energy linkage. So the linkage for the peptide bond comes from this bond here that is dissociated. So when the tRNA or the amino acid dissociates from the tRNA, during this step here, right in there, that's what that energy comes from. So protein synthesis requires 2 GTPs. One for either the IF2 or EFTU, and the other one for GTP, the elongation factor GTP. Okay? Okay. So I'm not sure I want to do this. I'll show you this. This just shows you the formation of the peptide bond. This is there's a catalytic site, a pocket in the 23-sRNA that acts as the catalytic site. And here you can see that here's the A site and the P site. So this is the carboxy terminal. This is the this is the tRNA with the amino acid attached to it at the A site, and this is the protein of the carboxy terminal. Here's the nascent protein, right, that's attached to the tRNA. This is the carboxy terminal end of the nascent peptide chain. Make sense? This is in the P site. It's attached to tRNA, so this is the protein. It can be as long as whatever. This is the carboxy end, and this is the amino end. And what happens in catalysis, right, is that this just puts there's a hydrolytic attack again on that carboxy site there. We form the peptide bond between this carbon and that nitrogen there. So the amino nitrogen of the amino acid attacks the carboxyl group of the peptide in the P site. Right? So the amino group there attacks that site. And that generates, now what we do, we form the bond now between not the tRNA, or not this tRNA, but it releases from this, and we have a peptide now, bond now between. Actually, it does not. This one attacks this one, right? And this is released, so the peptide becomes part of this. So now we have amino acid with peptide attached to it, and this tRNA on the A site now holds it all. That makes sense. The important thing that you realize is that this part here, 23S is the catalytic site. There's actually a pocket in there. The amino nitrogen of the amino acid attacks the carboxyl group of the linkage of the amino acid in the P site, and it changes the linkage. You have that. Okay. That's all I have to know. That just shows you again. I'm not even going to do that. Okay. So elongation now. I wanted to show you elongation. This is sort of what this is kind of what